Hello, it's Green's theorem time. Uh, I find Green's theorem to be, up there with Stokes' theorem, one of the least intuitive, hardest theorems to, wrap your head around and see why it's working the way it's working. At least with spherical integrals and that kind of thing, you can picture all of the coordinates moving around and tracing out your volumes. But here, it's kind of like a black box, and we have certain steps that we have to do. And I'm definitely not the person to explain why Green's theorem works the way it does. All I know how to do is solve these problems. So that's what we're going to do. We know that Green's theorem generally says that the integral on the line integral of p dx plus q dy is the same thing as the double integral over the region enclosed by the curve of the partial derivative of q with respect to x minus the partial derivative of p with respect to y dA. And so we can apply this for essentially all of these questions, and we should be able to figure things out. So in this case, p is e to the 2x plus y squared, and q is 14xy plus y squared. And one of the things that can be difficult to figure out is when do we want to use Green's theorem and when do we want to just take a normal line integral. One thing that will give you a nice hint is if it's after question 12, it will generally be Green's theorem and not like if you've seen the last kind of test exam 2 material already go past, you're likely in Green's theorem, Green's theorem land. But more importantly than that, if we just take a look at this, what we're dealing with up here, it will be much easier if we're able to take this derivative or take the derivative of this guy here with respect to y and this guy here with respect to x, because as you'll see, we'll end up with like terms that we can simplify down. So applying Green's theorem over here, we're going to see that this integral becomes a double integral. We don't really, r, not a. We don't really know what it's over yet, but we're going to take the partial derivative of q with respect to x. That's just going to give us 14y, and then we're going to subtract the partial derivative of p with respect to y, which is going to give us 2y dA. So now let's fill in this with a dx dy. We see that x is bounded on the top by y minus y squared and on the bottom by 0, and you can kind of more intuitively see this if we kind of sketch out what this thing looks like. This is going to be a parabola running like that, and it says we're bounded by the y-axis and that parabola, so you can see a little easier how x is bounded on the bottom by 0. And then let's see, we're bounded by the y-axis, which is the line x equals 0, and this guy, so we can set x equal to 0 to solve for our upper bound on y, which is, our upper bound on, yes, our upper bound on y, sorry. So 0 is y minus y squared, which is y squared equals y, so y, whoops, not sure what just, oh, I got an email, sorry about that. That's y equals 1, so y is going to run from 0 to 1. So now if I make a little bit more space here, we can just take this integral and get out of here. We can simplify our integrand to 12y, and taking this dx, well, we have no x's in here, so we can just multiply this guy in. So this is going to be 12y squared minus 12y cubed, integral from 0 to 1 dy, and this is going to be the same thing as 4y cubed minus 3y to the 4th on 0 to 1, which evaluates to 1. use Green's theorem to evaluate this line integral here, where C is a triangle with these vertices and a counterclockwise orientation. So it's always scary when they bring up this kind of thing, but they're being nice to us here. Well, it's scary only because you expect one, for them to be able to spell the word orientation right. Orientation. Yeah, that's no good. But more importantly, them bringing up the orientation makes it easy if they were to put, like, if the correct, let's say the correct answer is 8, I can't remember if it is or not. If they had a -8 over here, it's very easy to either guess incorrectly or come up with the wrong orientation. And the way that we remember it for this is that our counterclockwise, we're looking for counterclockwise orientation. That will give us the sign that we expect to get with our normal Green's theorem method. If we see clockwise orientation, we'll likely have to flip our sign at the end. And so let's see. We know that what we need to do for Green's theorem is to take the derivative of this with respect to x and take the derivative of this with respect to y and subtract this guy from this guy. So let's do that. We're going to get the double integral over a. Nope, I keep doing that. I'm not used to writing these. The double integral over r of 4xy minus 2xy dA. So we can simplify this guy down to just 2xy, bring that dA back in. And let's figure out what our bounds on integration are going to be. We can graph our triangle over here with vertices 0, 0, 2, 2, and 2, 4. And we see that we're looking at this scalene looking thing, which is going to, we can kind of draw two lines. One is going to be y equals x, and the other one is y equals 2x, that are kind of bounding this shape. And then we can say, well, looks like x is bounded on 0 and 2. So that's a pretty easy way to get, extract that region right there. So like we just said, we're bounded dy by x and 2x and dx by 0 and 2. So let's take this integral. We're going to get xy squared on x and 2x. This will be 4x cubed. Yep. And this guy will be x cubed. So now our integral has been simplified down to the integral from 0 to 2 of 3x cubed, subtracting this in, dx, which is going to be 3/4 x to the 4th on 0 to 2, which will be 12. Okay, let's suppose that f of x and y is some function p of x and y and some function q of x of y, and that the partial derivative of q with respect to x minus the partial derivative of p with respect to y is is 2 for every xy in the xy plane. And then we have this curve here, and we might as well, this path, we might as well draw it out. It's 3 cosine t, 3 sine t from 0 to 2 pi. So we know that that is going to be the circle with radius 3, oriented counterclockwise. 3, 3. So we know that we can turn this f dot dr into a double integral dA of partial q partial x minus partial p partial y. And this gets really easy really fast once you figure that out, because they give us partial q partial x minus partial p partial y. So now we have the double integral over r of 2 dA. And well, we could do this and figure out we could do a polar integral here, but we could also just say, okay, we know that the area of a circle with radius 3 is going to be 3 squared pi, and that's just 9 pi, and so we can express this as 2 times 9 pi, or just 18 pi, and we're done. Okay, we're using Green's theorem to evaluate this guy, where C is the boundary of this rectangle. And so many coordinates there is a little confusing, so let's write it out. We have 0, 0, 2, 0, 2, 3, and 0, 3. So we're dealing with this 2 by 3 rectangle in here. So we know that x squared dy, if we apply Green's theorem to it, is just going to give us the integral over r of 2x dA. And that's because this is essentially like having 0 dx plus x squared dy, and we know that when we apply Green's theorem, this guy goes over here, and this guy goes in to replace it with the sign flipped. And you can see how that would give us x squared dx plus 0 dy, which will give us our 2x that we already found. And since this is a rectangular integral, not just rectangular coordinates, but like a literal rectangle that we're integrating over, we can just put dx, dy, x is running from 0 to 2, y is running from 0 to 3, and we can evaluate this real quick. So x squared on 0 to 2 is going to be 4, and the integral from 0 to 3 of 4 dy is going to be 12. Okay, we are finding this whole thing where C goes counterclockwise around the trapezoid with these corners. So first of all, before we do anything, let's figure out what this trapezoid looks like. 0, 0, 0, 4, 2, 1, and 2, 3. So we're dealing with this kind of shape here. And you can see this would be pretty easy to do a rectangular integral over, because there's a defined line that we enter the region at, parallel to the y-axis, and a defined line that we leave the region at. And then the bounds on x are just its extrema, like normal. But importantly, we are going clockwise around this trapezoid. So we're going to do everything normally and then flip our sign at the end. Okay, so going on with the normal Green's theorem kind of thing, we notice that they have this in a little bit of an interesting form. They have dx before dy. So let's rearrange this thing. It's the integral over c of negative 2y dx plus x plus y cubed e to the y dy. Okay, so this is looking a little more like something we can deal with. We can apply Green's theorem really quickly and see that this will be the double integral over r of the partial of this guy with respect to x, which is just going to be 1. And then we are adding the partial, we are subtracting the partial of this guy with respect to y. Well, two negatives, we're going to get a positive, we're going to add 2, dA. So now we have integral r 3 dA, and we can actually find this integral manually. We don't have to go in and do all of that integration, even though it would only be a double integral. It's still interesting to figure this out. So we know that our points are 0, 0, 0, 4, 2, 1, and 2, 3. So we can kind of split this up into 3 different regions. Each of these triangles are going to have a base length of 1 and a side length of 2, so we can pretty quickly see that the area of this guy right here is going to be half of the rectangle. So its area is 1. So we have an area of 1, an area of 1, and then this is a 2 by 2 by 2. So this is going to be an area of 4 in here. So our total area is 6, and so 6 times 3 is going to give us 18, but we have to be careful because remember we're going clockwise around the trapezoid, so we have to flip that and get negative 18. And I'm going to go quickly check because this thing always scares me when it's clockwise instead of counterclockwise, etc. So I'm going to go make sure that that's the correct answer, and I'll be right back. Okay, I just went and checked. B is correct. So that's pretty good. And let's keep going. So according to Green's theorem, which of the following line integrals is not equal to the area of the region enclosed by a simple curve C? So I just have Green's theorem written out here, and we can use a little trick given that to figure out these guys. So we know here that, for example, this y is going to be assigned, given that we're calling whatever's dx p, we can assign p to negative y, and we can assign q to x. And what we're looking for in all of these answer choices is for the integrand and the coefficient outside multiplied together to add up, not add up to, but to give 1 as a final answer. And the exact reason why, again, something about this relation makes that true. I'm not exactly sure what it is. I had to go in and get help from in one of the math resource room session things to get this figured out because it's really not that intuitive for me. So I really wish I could give you a better explanation, but this is just how it goes. So we can assign p to negative y and q to x, and we can solve all of this. So going over here, partial q partial x is going to be 1 minus negative y dy, which is going to be negative 1. And then we have the double integral r dA, and we have a 1/2. So actually, I do get, this is why I do this, because sometimes it just clicks for me. I do get why this makes sense, because this gives you the area, because if we get rid of this 1/2 and divide everything in here by 2, we'll end up with 1 dA, and the integral of 1 over r dA is just the area. This in English is exactly that. So that's kind of cool. I like it when it clicks. That felt nice. But let's make sure all of our other answer choices work like that. So A definitely works. Okay, x dy, that is the same thing as saying q equals x. So partial q partial x is going to be 1. Our coefficient out here is just 1. So this is 1 dA, and that is also wrong. And the same thing applies for negative y dx, because assigning that to p, the double negative of y dy is just going to give us 1. Moving on, we have 1/3 y dx plus 4x. So q in this case is going to be 4x, and p is going to be y. So partial q partial x is going to give us 4, and partial p partial y is going to give us negative 1. And so D works because we divide 3 by 3 and we have 1 dA. So finally, let's hope this one doesn't work, because if not, we're going to have to go back and figure out what went wrong. We have P is equal to 4y, and q is equal to, sorry, q is equal to negative x, and p is equal to 4y. So then applying partial q partial x, we will get negative 1, and we get minus 4 for partial p partial y. Dividing that by 5 doesn't help because this is the negative area, which is nonsensical and is also the correct answer, though. So there we go. And we're done. Hope that was it. Hope that was helpful for you. This was the best thing I've ever done for myself in terms of understanding this Green's theorem stuff, and I hope a tiny bit of that maybe got over